Alright, so we're going to continue chapter 3, part 2. And again, video lectures are kind of, they're not YouTube video, okay? They're just, we're using the PowerPoints as a board, alright, whiteboard. So it's very much the same as you looking at the board in the classroom, okay? And it's better than the classroom because now you can see it clearly. All you have to do is just zoom out and you can see it, yeah? Make it big, I mean, yeah. And so let's get into application. So we're going to apply geometry tolerancing. Don't feel bad about this word, okay? Just tolerances. You can go with the limit or something, and whatever way, whichever term is going to make you okay easy to understand. Use that. You don't really have to stick to this. They was just talking about different limits for different shapes, you know? And we're going to apply that. Okay, form and profile tolerances. They control each feature, size, and shape. So form and profile, they control the size and shape. Okay. When we say form and profile, remember that we're talking about the tolerance, the limits. Okay. Form and profile tolerances, they're gonna control the size and the shape because form and profile are the shape, right? So your straightness, your surfaces are lines. So therefore you have to know that they will definitely control the size of the part, okay, and the shape of the part. And we call that form and profile tolerance. So if we're dealing with the shape of the part and you're measuring, okay, that part, you're dealing with the size of the part, you're measuring that part, okay, you will have to refer to the limits, okay. So what kind of limits? You will refer to the form limit and a profile limit, and follow that in order to make your right or correct measurements. Alright, orientation, location. Again, Runout your rotation style tolerance. They define the relationship of individual features of a part, okay? So if we think about the orientation or location or the rotation or Runout, okay, tolerance, we're talking about the relationship. It's got to be a relationship because orienting something, right, or locating something definitely need relationship because you can't say where that is, okay, and where that is without a relationship to something else, yeah. So for form and profile, size and shape is an entirely different thing. They can stand alone by itself, right? The size is the size. We're not talking about where that part is. Here for orientation location, we're talking about where that part is, right? So therefore, that kind of tolerance is definitely dealing, all right, with the relationship or individual features of that part, okay? Because you have to locate the location of the component in that part and vice versa. So right now you can't be able to see it, okay, in your brain, but we can use common sense to understand, right, the logic of the orientation, location, and rotation around 360 is your Runout, right, circular or not. That's totally defined, right, relationship of individual features of a part. Okay? Okay, so here we have geometric tolerancing. So instead of 6, they're grouping into about 5. But actually, this profile, I wouldn't group it under a form because that's a separate thing. So I'm just going to go this as alright number 5. Anyways, form, orientation, location, we have Runout, and we have a statistical, right, and then a profile. Form, these are your characters, and then characteristics right there, and then characteristics right there. Okay. And then we have another characteristics for that. So just refer to that table, right, in your previous part 1. And right now, all you have to do is to know, all right, that. Okay, form tolerances. Some people again use just tolerance, and some people use the tolerances. In this textbook, this is using tolerances. So how far an actual surface or feature is permitted to vary from the desired form. So whatever we're measuring or inspecting, most of the time we're just inspecting our product, alright? And if that product is conforming to the product standard product, so and we call that size and shape. Okay, if you're checking the size and shape of that, that's got to be not so alright different from your standard form. This is your product. Let's say sample that we're checking. Okay, we pick sample out of the product lot and then we inspect them and see if they are conforming the standard alright size and shape, and that's what we call checking the form tolerances. Yeah, so this shape and size got to be about the same as this, right? I shouldn't say about, got to be this, right? And it shouldn't be over that tolerance zone. Okay, got to be within it. So we're just looking at, if they are permitted to vary from the desired form. So when you take a look at the diagram, we usually draw this way, okay, to indicate the tolerance. So here's straightness and then flatness. It's a little bit different. The straightness is right here, okay. Here we're looking at a surface, and here is our tolerance, 12.5, okay, and we can go to 12. So that's lower limit and that's our upper limit. Okay, here you can see we're checking straightness because of this little symbol here. So refer to the table for the symbol, and here is the value, alright, of that straightness. Okay, got to be 0.02. Okay, 0.02. So these are the permitted, alright, value. And then we go here, another straightness, because my symbol tells me that's what I'm looking at. And it's got to be your diameter again, got to be 0.03, alright? Tolerance. And we're going to apply that straightness to an axis right there, okay? And right here, we're applying the straightness to a surface. Surface. So if you take a look at it mathematically, you gotta go slow to be able to see it. I'm gonna point that out for you right now. So here you see that's a difference of 12.5 and then 12.0. So 0.5 is your tolerance limit, okay? So that's lower and then the upper. So here axis meaning like how straight your axis is, okay, the central core. So that's what we're dealing with this one, okay, what is this? And surfaces, okay, the surface, right? So we're looking at that thing right there like that. Okay, here is your circle. So we have an axis meaning the core, okay, of that shape. And then we're looking at the surface, this surface, okay, that surface. This is a 2-dimension. 3-dimension is going to be a 360-degree around, okay? So your surface is a circular, pretty much. If you cut it in 2D, you see it this way. So if you cut it that way, you're going to see that little circle. Okay, if you cut, alright, slide it down from the top like this way, you're going to see this. Yeah, so this is your surface and that's your axis. The straightness got to be 0.03, and then the surface all around 360 is going to be 0.02. It's got to be that straight. Okay, and that is the acceptance or permitted value for this shape. And we're checking at the straightness. straightness of the surface. The straightness. It's got to be straight. It's got to be straight. Okay, and you can come up a little bit. So if you see the surface, it's got to be like that. However, your tolerance zone can go this little. Okay, 0.02 up, so like that, or down like this. Okay. Yes, and the same thing. The core, center core. Okay, can go 0.03. It's a very tiny little thing. You can see, even if it goes up this much, you can see the difference with the naked eye. Okay, you have to use a special instrument to detect that. So this side and then that side, so that you can come down a little bit, which is 0. Okay, can go beyond 0.03. Can go beyond 0.03. Okay, two. So that's my the true axis is right there. So your axis can be around here and around here. So it wouldn't give you any kind of difference because you're within the tolerance, right, zone right there. So when you see this, you will see the diameter here. So how is it saying? So this little circle is right there. Yeah, see that? So the diameter from here to here, okay, is 0.03. See that? Okay. So it's really difficult to draw it. So I should draw it this way, and then draw a real big thing like that, and then I should draw like this way. Okay, your axis, okay, can be this big. Okay, it can vary this big. So from here to here, it's set. Okay, is 0.03. That diameter is 0.03. So therefore, the straightness got to be okay within this. This picture is so exaggerated, so it looks like, alright, your axis is so big. It's not like your axis is real small line, okay? And this is a very tiny little diameter, so very small circle that we're drawing, but in an exaggerated way. So anyway, you got the idea. But your straightness can be like this. So this is over, yeah, over the circle. So your axis is too big. Because it's beyond the alright permitted zone right here, which is 0.03. Okay. Oh, diameter. I think you see it now. Take some time, okay, for you to be able to see it. So please take time to see that. And the same thing for flatness. So I'm going to go real quick for you now. So here we're looking at the very first one that you see in the frame. This right here, your control frame symbol. Yeah, so that's the flatness. So we're dealing with the flatness tolerance, and that flatness is going to be 0.5, meaning like it got to be, okay, 0.5, okay, flatness, and it can't go beyond that. And the difference, all right, for this straightness and the flatness, when you take a look at it, right, even for this too, I want you to pay attention. Okay, here we're dealing with the axis. Yes, totally line it up for you, underline this for you, so you can see the diameter right there. See, okay, because you're dealing with axis is a circle thing. Yeah, here surface is just one, right? It's just a surface. Okay, even if for this guy, right, the shape is not a rectangular. This is telling you the surface that we're looking at is that, and the axis is going that way. It's kind of like a cylinder, but it doesn't say cylinder, so we're dealing with maybe a component of a part. Okay, because there are many different kinds of shape. So if you think about a product, let's say a chair or something, okay, and they have like a different kinds of shape right there, even the leg of a chair, okay, and here's a chair, the leg of a chair, you have a straightness right there. We also have an axis right there. So anyway, so you know that this is the axis, okay, and that's the surface. So even though the surface is still, okay, we can see in the circle when we talked about the surface, that's going to be a regular, all right, value 0.02, meaning like the surface got to be straight, all right, that value, okay, can go over and under that. Otherwise, your surface will come out dented, okay, or won't be smooth. All right, for flatness, the same thing, okay. Your product surface got to be straight, and also it's got to be flat to certain, all right, value, and that value is going to be here in this case is 0.5, all right. And I want you to try to get that, all right, what it is outside to read instead of just getting the number and the symbol. So dealing with the flatness is 0.5 flat, yeah. And this is a very exaggerated picture anyway. Flatness tolerance zone, very, very exaggerated. It's definitely not like this. It's like this, okay? Naked eye will see it that way, not this way. This is like very, very, very exaggerated surface, and definitely not dented like that. It's straight like this. But that 0.5, we're trying to point out 0.5 is a very minute, right, value. So therefore, that surface got to be flat, okay, within that zone. Okay. Again, this is a linear we're talking about, a linear. There's no pi right there, so not a circular thing right there. So be very careful with your geometry. Alright, and then now you get the ideas. Every time you see this big, alright, exaggerated, alright, drawing, your surface is not this, your surface is this. Okay, it's pretty straight and pretty flat. We're just saying that all the imperfection on, alright, we're talking about 10 to the power minus 26 kind of, okay, smallness that we're talking about. And it's got to be within that zone, yeah. And it's very important because nobody want to buy a dented table, right? You want pretty smooth and shining and flat, right? And straight table. You don't want a curved table. Nobody want to get a table like that, right? Everybody want a table straight and flat. Yeah, so you can write and do your stuff right there. So anyway, so therefore we go into the micro world, right? Micro, very, very small exponent, negative exponent, okay, number right there we're talking about. So the manufacturing is that powerful, yeah, and we're taking everything for granted. The development of a product has incredible amount of science and precision in there, and we call it precision engineering. Without that, you will have a bad product and nobody want to use it. Okay, so let's go to the next one. So now I'm gonna go real fast for now because you get it, I think. So here, circularity, the same thing. Little symbol right there, that's your circularity. Common word roundness, alright, and we wanted 0.4 exaggerated picture. We want this circularity, we have perfect circularity, and okay, this got to be 0.4, okay, 0.4 wide in order for us to have a perfect circle right there. If you go beyond that or under that, your circle is going to be D-shaped, okay? Alright. The same thing, don't pay attention to any of that. This is just showing you, okay, a drawing for a cut section, which is a little bit different, and we don't have to deal with the part right now. All you have to do is understanding the frame right now, okay? So now I have a frame, and I'll take a look at the frame, and you see this, and you should know that it's telling you the cylindricity, alright, telling you the tolerance is 0.2, okay, and that cylindricity got to be within that tolerance, which is from here to here is 0.2, okay, wide, from here to here, see that little arrow showing? I also draw this for you right there. And don't pay attention to this side yet, okay? we're concentrating on this side, okay, for your course. All right, next one. Profile. So profile is every time, right, the direction changes. So here we have straight, 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 and then we start curving with an angle out, and then go back, and then change again here. Change here, change, 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 change. Okay, right. So it looks like a football field, and we're gonna come to our control frame right there. We know that's a line. We know we can go. Okay, the wideness got to be 0.8. Okay, tolerance zone right there. So I can draw like this for you. Okay, so your line got to be within there in order for it to be shown as, you know, a perfect line as that for this profile. And you can go over this or under that. It's got to be within this zone. That's we call that a permitted zone right there. All right, now profile tolerance surface. Okay, the same thing. You have profile. Profile means like you have a change in direction. See that the part, whatever you're measuring, has a change in direction. So therefore, we call the profile. And it is a surface. It's not a line like that. Okay, you're completely, and you have a datum point that you are measuring that surface. Okay, from. So here, surface, your value can go over 0.5 or lower, and this is your data, which is now, okay, a plane. Okay, so if you look at the very small description here, you can see profile over surface and bilateral tolerance. This one is a unilateral tolerance. Okay, and this is profile over surface, unilateral tolerance. Profile over surface, bilateral. Bilateral means on both sides. Okay, like this. You can see that's our true surface. That is the zone that we can go up and down. So we can go over 0.5. Okay, so therefore this side is 1 and that side is 0.4. 1 means like 0.1. Okay, that's 0.1 on this side and 0.4 on that side that you can go up and down. So we call that bilateral, and this is only unilateral, meaning like this got to be 0.5. That's also uni. That, okay, got to be 0.5. This is a bi, but then it's not showing the exaggerated zone for that. Yeah, you can divide in any way you want. You can do like 0.25 on this side and 0.25 on that side. You can also do 0.2 on this side, okay, and then 0.3 on that side, whichever way you want to do. But that's not the case. The case is when you take a look at the frame, control frame, you should understand the symbol. So go back to the table and study that, and you should understand the value. You should understand, okay, the datum, where you're measuring from. So if you take a look at this, now you should know, if I ask you what is that, you should know that's a profile line, that's a profile surface, and my zone is 0.5 can go, okay, beyond that. Orientation, angularity, okay, the same thing here, dealing with angle is my pointer. And we're dealing with, again, axis right there. Okay, here is the angle. It is a cylindrical angularity tolerance zone. So here right there, 0.2 wide diametrical tolerance zone. This is your tolerance zone right here. Yeah. Again, your control frame right there. Angularity, my value, and then my datum point I'm measuring from here. Right, we're measuring 45 degree. This part feature is from this datum. Yeah, this guy is just showing you right here the axis. Okay, circle right in there is 0.2. I think it's just more. Okay, now here angularity tolerance surface. Okay, here is the surface. That surface is measured from this datum. It said it so. Okay, is the angularity. that surface is at an angle 20 degree, okay, from this datum point, which is your plane, horizontal plane, and it should go only 0.3. Yeah, I think now you know how to read it. Now drawing that same thing for your datum, 20 degree from that point, measuring from here, your surface, okay, can go only 0.3 wide at tolerance zone. Because if your surface is like so big, and if it's okay going up like that, like this, that's a bad surface. Yeah, it should be within that. The surface should be within that zone. We expect the surface to be within that zone, 20 degree away from that plane. Alright, next one is perpendicularity. The same thing, but this time our angle is going to be 90 degree. Yeah, so we go here. We have a datum right here, plane, okay, coming from here. It's going to be that much away. Yeah, and 90 degree, perfect 90 degree right there. So on this side, it's, and they show you the angle right there. See, that's your datum. So that's 90, perpendicularity right there. And here is your zone, 0.6 is set as zone. Yeah. The next one, axis. So here, my axis is right here. And here's my zone right there. Okay. And there's a datum point that we measure from, which is here. Okay. And that got to be 90 degree. Okay. To the axis. This is my axis. Yeah. And here you can see the 90 degree right there. Parallelism. So now we're seeing parallelism symbol right there. My value. My datum is right here. Here is where we're checking the parallelism right there. And this is our tolerance zone, which is that guy. Okay, 0.4. Parallelism surface. So here, this is my surface. My control frame, parallelism here. My zone, 0.2. Datum is right here. You're checking that. Okay, parallelism. And that parallelism zone is like this. Okay, it can go between here and here is like really exaggerated, so you thought like, oh, it's not parallel at all, but it is. Okay, it is just too big. Yeah, you're just seeing the surface a little bit or the bulge on that side, but it's pretty good. Okay, it's land on 0.2 right there. Okay. So as a university student, you gotta do everything you can to be able to see or imagine or understand with your mind for very small things. Okay, like you in the space is not you alone. Okay, you in the space is you surrounded by so many little particles. Okay, and we call that atmosphere. So you're surrounded by a sea of nitrogen, which is your N2, which is your inert gas, and that's the 78% around us that we're breathing in and out. Okay, we're not breathing only oxygen. So don't get wrong on all of that. You're breathing oxygen, and most of them are 78% nitrogen. And two, it's not affecting you because they are inert gases. Okay, so the same thing with that. Okay, even if you see the surface like that, for our eye, it's pretty, like good parallelism. But then if you exaggerate it, go into the material zone, which is your little particle chemical element zone, you can see the imperfection of the surface. Yeah. All right, so let's go to the next one. So in this case, we're getting into position, because you can see this little GPS little thing right there. So that's the position. Oh, where's my position? So now if you have a phone, we know exactly where you are. Yes, you have to kill your privacy off if you don't want anybody to know where you are. So anyway, so here we have a material, yeah, multiplier condition right there. And then our datum is right there. We have first, second, and the third datum here. That's your primary, secondary, and tertiary datum. So here is the first one, second one, and then the third one. Again, so every time we're dealing with position, location, you have to understand that you're dealing with a relationship, okay, between the part features. Okay, so now we're getting into here. So we're looking at a circle right there, okay. Whatever unit that is, we have a diameter of 11, and it can go up and down 1.5. And we are locating that position from 3, okay, planes. From here, and then from here. So this is from here, okay, and then this is from here, and this is from here, that much, okay. That is going to be for B, far away. And for A, it's a little bit difficult for you to see because this thing is right in here, yeah. It's a section that we're cutting right straight down. Okay, not like this way, not in the x-axis, we're cutting on z-axis. It'll be difficult for you to see it. Anyway, don't worry about it. Just try to know what you're reading here is fine, yeah. And it would hurt your mind to be able to see this diagram. If you can get this, I'm quite happy. So anyway, so 0.6 here, and then the datum plane is right there, right, primary and secondary here, that far away, and then this far away, and you can be able to locate a position, which is that. Alright, the next one, bonus tolerance. It's nothing but you minus the manufacturer's size from your maximum material condition. So the bonus tolerance is nothing but you just showing you the differences, okay? And that's we calculated by subtracting the manufacturer size from the maximum, which is our maximum material condition max, which is here 8.6. They always give you this table, right? You'll know the least and then the max. So the least is 8.2 and the max is 8.6. And those are all your manufacturer size, and all you have to do is minus this right from the max, which you will get this, yeah. So that's your bonus tolerance. Bonus meaning like you can go a little more, yeah, little more over for your measurement on whatever product that you're designing. In order to conform with the standard, you can go a little bit more this, yeah, and we calculate the bonus that way. Especially for these, if you want to speed up the production, we cheat this way a little bit, yeah, because the time that you do to produce a product is money. So if you can increase the speed of your manufacturing, okay, processes, you can make a lot of money. So therefore, they allow the bonus tolerance this way. Okay. Also, we can do a lot of bonus tolerance because we don't want like bad quality products or a D-shaped products. We don't want that. So we still want perfection, but then we try to see how much can we, all right, speed up by allowing bonus tolerance in this way. And because the more precision that you do, you're spending more time, right, in product design and also production. So therefore, we use a bonus tolerance. So how do we calculate? We calculate this way. Yeah, 8.6 minus 8.6 is going to give you 0. And then 8.6 minus 8.5 is going to give you 0.1, so on, so all the way down. Yeah. So I'm going to draw that for you. This is how you calculate, and here is your MMC. Okay, MMC minus the manufacturer part is right there. Manufacturer size is right there. Okay, but that's still pretty good because it's still within the permissible zone. Alright, so positional tolerance allowed this much, okay? So all you have to do is you add this and this. So you added this and this, and you're gonna get that. Yeah. Now we have a little more, not like as precise as this, so that we can save and earn more money here by speeding up the manufacturing processes. So anyway, so let's go here, another frame there, position again. And here with also dealing with the cylindricity of some sort, material condition is there for you. So here how we calculate the bonus right there, manufacturer side is there, and your max is right here, this number. And then you do the math, which is this guy, and you're gonna get the whole thing. You're gonna add this and that, and you will get this. Okay, all right. But for the education purposes, all you need to know is how to get a bonus. You know, I'll give you this and I'll give you that, and you should be able to calculate this. Okay, let's go. Concentricity is another frame right here. You look at the symbol right there, and that's your concentricity. And here again, concentricity is everything. The diameter is coming in on 0.1, and that's your zone. And then that's we're gonna measure from this datum point. So if you look at the concentricity tolerance zone in an exaggerated way, you're going to see that, yeah? And this is your tolerance zone, which is that guy right here. Okay, now I think you are pretty good at looking at the control frame and read it with the diagram symmetry. Here, my symmetry symbol value measure from here, yeah? Exaggerated. So the symmetry got to be, that's the shape right there. Got to be like this, yeah? 0.7 wide tolerance zone for symmetry. So that's a play around area right there. We can go beyond that. It won't be symmetric, yeah? Alright, let's go next one. Circular, less complex. So this is a runout. So if you take a look at runout, because it's a 360-degree round, yeah, we're doing that. So they include the circular or total, and they both require data and reference. So here in our case is A. It's here. Your frame. We know that's a runout. It's not a total because it's only one line right there. So that's a circular runout, okay? And it's going to apply, it is applied regardless of the feature size, so your R, L, and S. So we don't have to worry about the max and least. So what it does is it controls the circularity. Okay, it also controls the coaxiality. Coaxiality is nothing but feature. They are sharing the same common axis. They're sharing the common axis, right? Complicated part that you would produce. When we say part, don't think about part. Part mean like a component of a product. Okay, even manufacturing a desk. Alright, if you really think about it, it's very complicated. Very, very complicated. Even if you're producing it, you know. If I tell you to go ahead and build your own chair, and you have to start to measure and try it, maybe you can come up with one. You know, I tell you to build the same one, you're gonna have an issue. Yeah, and I want you to try it. Okay, if we have like time, I will, okay, I'll give you a project like that. Instead of studying the whole thing, I'll give you one project for the entire semester and ask you to go ahead and alright, to build one, design a part and a design product and produce 6 the same thing with your head and a part, and apply the metrology to measure all of the inspected, and you're gonna have so much issue to come up with horrible thing. So anyway, so tolerance is that, okay? So in order to produce the same product as your design, you have to have a very good tolerance so that your product will conform to the standard. It will look alike, okay? They won't come out like whatever. Every time you produce something, come out different shapes. That would be the end of the world. Okay, anyway, so let's go. I'm not going to get into this detail because it's just a waste of time for you to see it. I want you to get this, okay, understand the frame. So understand that this is for the Runout circular, and then that's your datum you're measuring from, well, right there, sorry, and that's, okay, is your permissible zone right there, functional zone. So I'm gonna erase that. Okay, go next one. Now the total Runout, next Runout is total right here. So it's more complex. So circular is the least complex, and this is more complex because we're dealing with a circular and profile. Profile is the one that changes the direction. So anyway, just concentrate on the frame. Total Runout 2 errors. That's okay. The zone right here, 0.2. Don't go over that. And we are measuring from a datum point, which is your plane right there. Yeah, which is this guy right here. That's, yeah. Okay, so if you can get that, I'm quite happy. I think there shouldn't be any kind of issue. Alright, stat is just like dealing with, okay, program, like we use Minitab and similar software. Pretty easy. All you have to just put data in and it will spit out all the data tables for you. Status, nothing but it's just a tolerance that controls a variable aspect of a feature. We're looking at the variable. Variation is so important, and we use stat to get that variation. It controls a variable aspect of a feature using statistic and statistical process control. We call that SPC. So that's, you sit at your table and then you check your process, okay, production and processes, and then they have to be within the specification limit that you determine. And if they go up and down, meaning that there's issue, and you're going to find the issue and solve it. Yeah. So quality folks, so my line is to solve issue, and you monitor, okay, most of the time monitor, inspect, and do policing. Alright, addictive tolerance is nothing but we usually add up because it is called addictive, meaning like add it. Okay, add it up. So add it up, interchangeable, right? Manufacturing, meaning like we're adding the tolerances as again for efficiency and also to increase speed, and also other purposes. Anyway, so that's the end on chapter 3.